Hello and welcome to a new ADF tutorial, and today we are going to look into the last of the spectroscopy options that ADF has to offer, a VCD spectrum. VCD, or vibrational circular dichroism, is a spectroscopy method not unlike infrared spectroscopy where vibrations are key. However, instead of looking at dipole strength, as is the case with IR, VCD looks at electric and magnetic dipole transition moments. What this means is that VCD will be able to differentiate between different enantiomers, as these bend circularly polarized light differently. Alright, let's get into it. First we're going to draw oxyrain, which is an epoxide, the most simple epoxide that's known. There we go. Now we're going to add hydrogens, atoms, add hydrogens. Now, this is a symmetrical molecule, and since we will be looking at enantiomers, we need stereocenters. So we change 2 of the hydrogens to deuterium atoms. And we are going to do that by selecting the hydrogen atoms, by holding the shift key, and then go to atoms, details, and change the mass to 2 in these fields. Once that is done, you can go back to the main menu and we will pre-optimize the structure. When that is ready, we will change our task to geometry optimization. We will change our functional to GGA BP86. And our frozen core, we will remove it to none. Alright, now we are going to run our file and save it as oxyrain. Alright, the calculation is finished, and now we are going to read the new coordinates. Yes. What we are going to do next is change our task to frequencies, and then go to properties and press VCD. We are going to check the box and move back to the main tab. Now we can run this job and it will ask us to override. We can press yes. Now it will run this job and make our VCD spectrum. Normally this doesn't take very long. And after we have finished, we can visualize the spectrum and analyze it. Alright, as you can see, the job has finished. And we will go to Spectra to view the result. Here we have our spectrum, our VCD spectrum. And here we have our oxyrain molecule. So, we are going to analyze this peak, this large negative peak, at about 3100. We are going to analyze this normal mode, this vibration. And first of all, we are going to sort our EDTM values. So our highest are at the bottom. Alright, now we will select the atom with the highest electric dipole transition moment. And we go to VCD tools and press default visualization for GCO analysis. This will make 2 of the atoms larger and arrows will appear. With the up and down keys you can change the size of the arrows however you like. Next up, we are going to group the most important functional groups in this normal mode, which are the largest ones, which is this CH bond. We can select them both by holding down shift and group them by go regions and then set selection as new region. We are going to do that with both. You can also press Ctrl G to group them as well. Next up, we are going to see how these groups contribute to the entire normal mode that is depicted in this peak. And we are going to GCO Now, a window will pop up and it will show us some information. We scroll all the way to the top. And fragment A and fragment B we have just selected, fragment A and fragment B. And this is the normal mode 15, which we are looking at right now, which is the peak at 3100. And it is, you can see that is this one. Now, as you can see, fragment A and fragment B contribute the most to the electric dipole transition moment, while the rest of the molecule is almost negligible. And the same is the case for the magnetic dipole transistor moments. Localization of this normal mode is almost completely on these fragments, that shows the importance of these functional groups in this particular normal mode. Feel free to experiment with different normal modes and different functional groups, and with all the other settings the user interface has to offer. That was it for this tutorial on how to visualize the VCD spectrum. You could use these spectra to compare with experimental spectra to identify which enantiomer you have produced in the lab. I hope this tutorial was useful for you. If it was, please leave a like, and please let us know in the comments down below what tutorial you would like to see next. Take care.